Hello, I'm Jason. Welcome to this lesson in the Laplace transform tutor. Here we're going to learn how to take the Laplace transform of the cosine function and also the sine function. They're going to look kind of similar. What we'll do is we'll apply the full-blown integral to the cosine and we'll do that solution, and then along the way we'll kind of pick up the sine function as well. I don't think I have to explain to you how important sine and cosine are. They're going to pop up in almost lots and lots of problems that you do. But what we're going to do is derive it straight through the integral. Gives you practice with doing that, also sharpens your calculus skills. Now I am going to say that it's unlikely that you would probably see exactly how to do this unless you see it once. Sometimes, derivations, you do them and you're like, oh, that makes sense. But if you had just stared at this yourself, it may occur to you what to do and it may not. So what I'm going to do is go through the integral, assuming that you don't know anything, and just explain everything step by step. All right, so let's say you wanted to find the Laplace transform of cosine beta times t. Now this in your book could be anything. You could say cosine AT, cosine BT, cosine whatever, but there's a constant in front of the t. Sometimes you might see it as omega if you're dealing with electrical engineering. There's usually a cosine in front, a number in front of the t. It's going to end up being the frequency of the cosine that you're talking about, but it's a function of time, and this beta is just a constant. That's the point to realize. So what we're going to do is we're going to apply the definition 0 to infinity e to the minus st cosine beta t dt. So again, if you know how to integrate this, then you're done. That's the Laplace transform. That's what we're going to do. What we need to do, though, is do integration by parts. And it actually turns out, if you remember back to calculus, sometimes you have to do integration by parts more than one time. You've done those kinds of problems back in calculus, and it's going to happen in this problem. I'm going to warn you. So we're going to fill up the board doing integration by parts once, then we're going to fill up the board doing it again. I know it's a little bit to get through, but these are kinds of questions that if I were a professor, I might ask you just as a bonus question or something, because it really shows me that you know your calculus. Now, doing these kinds of integrals in such detail are not something you have to do for every Laplace problem, but you do have to do it here. So let's go ahead and set up our integration by parts. So we'll say u is equal to whatever the exponent is, e to minus st, dv, we'll just say that's the rest of the integral, cosine beta t dt. And from this you need to derive other pieces of information that we'll plug in. So for this, let me write it in blue. For this, du, what is the derivative of this with respect to time? It's minus s e to the minus st dt, right? Think of it du dt. This is what you would take the derivative. The derivative of the exponent comes out, and then here we have an indestructible guy right there. And then whenever you're calculating what v is, you're integrating this. The integral of cosine is going to be a sine, but the 1 over beta is going to come out, and you'll have sine beta t. I'm not showing a lot of these steps because what's really happening is basically to get this, to get v, you're integrating both sides. You're integrating this to give you v, and you're integrating this to give you this. I think a lot of you guys have had enough calculus now. You can integrate a real simple cosine function to give you a sine, and what comes in here comes out as 1 over beta. So that's the setup for the integration by parts, and now we have to actually pull it off. So we say uv minus the integral of v du. U is going to be this, so we'll have e to the minus st. V is going to be this, so we'll have 1 over beta sine beta t. And then we go from 0 to infinity, because when we do the first part, we have to evaluate at those limits of integration right there. And then we have minus the integral, again from 0 to infinity, v du. So v is 1 over beta sine beta t. That's v. Du is this guy here. So I'm going to put a parenthesis so we don't get confused. It's minus s e to the minus st dt. If I didn't put the parentheses, you might think these were subtracted, but these are really multiplied together. So it's uv minus integral v du. All right, it looks really ugly, and in truth, it's really not that hard, but you do have to be cognizant of getting the signs and everything right. So what I'm going to do here is evaluate this at infinity and 0. So I open a bracket, and then I say, all right, at infinity, I'm going to have the 1 over beta, let me just put out in front, and then I'll have e to the negative infinity plugging in here, and then sine of infinity when I put infinity inside of that, right? And then I subtract off from that, putting in 0. So I'll have, again, 1 over beta from this, and then this will be e to the 0, and then this will be sine of 0. Don't try to do too many things at once. Don't try to evaluate all this stuff as you know, in one step. Write it down, and then in the next step, evaluate it, and you eliminate your sign errors that way. Now, what's going to come of this here? We have a minus sign, but we have a minus sign here, so that can be pulled out and made to be a plus sign. What's a constant here? Beta is a constant. S, it acts as a constant because we're integrating over time. We can't pull out the sine because it has a time, and we can't pull out this because it also has a time, but we can pull out S over beta, integral 0 to infinity. And just to rewrite things a little bit, I'll put the exponent first, e to the minus st, and then I'll put the sine beta t dt. So what we have done is we have come down and done our initial pass through the integration by parts. So let's go in here. What am I going to have here? Well, everything is trumped by this because the sine infinity is kind of impossible to really evaluate. But here, everything's divided by e to the infinity. So this whole thing goes to 0. Here, sine of 0 is 0. This actually goes to 1. E to the 0 goes to 1, but sine of 0 goes to 0. So this whole thing goes to 0. So again, everything in front is nothing. So this first pass through the integration by parts gives us this. Now this is not the answer, but I want to point out to you something, and I'm going to do it right here. It's not really a great place to do it. This is the Laplace transform of sine beta t. Just keep that in mind because we're going to use that fact later. In other words, the Laplace transform of a cosine gives you some junk out in front times the Laplace transform of the sine function. Notice beta's still in there too. So basically what happens is when you take the Laplace transform of a cosine, you get some stuff times the Laplace transform of a sine. We're going to use that fact later to derive what this is. I'm just pointing it out to you now, so keep that in mind. So what we want to do, let me kind of continue on the next board. Let me rewrite this so far. What I will do is I'll say that the Laplace transform of cosine beta times t is equal to s over beta, and then I have an integral 0 to infinity e to the minus st times the sine beta t dt. Now here's the part that you may or may not see. It's not something that you were just born with and you would just know what to do. It's just that sometimes when you do these kinds of problems, you realize that here I started with a cosine, and then I ended up with a Laplace of a sine, all right? And then you're stuck again because you're like, well, this is going to lead to nowhere because I can do this again, but it doesn't seem to converge on something like an answer because this integral looks to be just as complicated as the first one I started with. But then you start thinking back to your intuition when you learned about integration by parts. And since you have this cosine that ended up transforming into a sine, there's a pretty good chance that if you do integration by parts again on this, that this sine will flip-flop back into a cosine. And since this cosine beta t changed into a sine beta t, there's a good chance that if I do it again, this sine beta t will change back into a cosine beta t, and then I might be able to solve the problem. You may not be able to see the exact path to the answer, but you can see that sometimes when you do integration by parts, the complexity of the integral remains the same, but with these sinusoidal functions, they just flip back and forth, back and forth, back and forth, if you do it over and over again. So that's the intuition we're going to run with. And we're going to do integration by parts on this integral. So we'll have to, again, define a u, which would be e to the minus st, and a dv, which is sine of beta t dt. Basically exactly the same, or very, very similar to what we have done the first time. So then I'm going to switch colors again, and I'm going to say, all right, then du is negative s e to the minus st dt, same derivative as before, really. And then I have to solve for v, so I'm going to integrate both sides, and then I'm going to basically say, well, what's the integral of sine? It's a negative cosine, but I have this beta here, so it's negative 1 over beta cosine beta t. So when you integrate sine, you get negative cosine. That's where the negative comes from. That's where the cosine comes from. The 1 over beta happens because if you were to do this in a calculus 1 kind of way, you would do a substitution here, and you would do a derivative, and you would find that the beta ends up coming out as 1 over that. So that's basically what you get for v, and that's what you get for u, and that's what you get for all of these other things. So let's go and apply the integration by parts method. So I'll draw a line there, uv minus integral v du. So u is e to the minus st, v is 1 over beta times cosine beta t. U times v, I have to evaluate it from 0 to infinity, minus the integral 0 to infinity v du, negative 1 over beta cosine beta t v, and then I have du, which is this, and I'll open up a parentheses to make it clear, s e to the minus st dt. U times v minus integral v du. That's what you're basically doing here. And so, I'll switch colors back to black. Let's evaluate this at the limits of integration. So over here, at infinity, the 1 over beta, let's carry that along in front. Then I'll have e to the negative infinity from plugging infinity into here, and then cosine of infinity from putting cosine into the t, right here. And then I will subtract off plugging in the 0. So again, I'll have negative 1 over beta here, and then it'll be e to the 0, and there'll be cosine of 0. Okay? Cosine of 0, like this. So that's this, and we'll evaluate what that really boils down to here in just a minute. Let's turn our attention to the second part. So here I have a negative, and a negative, and don't forget this is actually multiplied together inside of here. So what's going to happen is I'm still going to have a negative sign here, because these will make a positive, this one will remain negative. I'm integrating over time, so this s is acting as a constant, and this beta is acting as a constant, just like before. So I'll pull out s over beta, and then the integral sign remains from 0 to infinity, and then e to the minus st comes in, and then cosine beta t dt. And look, exactly what we suspected happened. We did the first one, and it changed into a sine. We did the thing again, and it changed into a cosine. And believe it or not, this really helps the situation. Because let's evaluate the limits of integration right here. E to the negative infinity is going to drive this whole thing to 0, no matter what else is there. All right? When you see e to the negative infinity, it's going to drive to 0. When we have this, e to the 0 gives you 1. Cosine of 0 also gives you 1. So actually, this whole thing, including the negative sign out in front, is going to give you 1 over beta, like that, 1 over beta. So we have negative times negative gives me a positive, 1 over beta. This becomes a 1. So that's what this whole thing is going to be, including the negative sign out front is going to give you that guy right there. And then we see that this integral transforms back again. So at first glance, you might look at that and say, the integral doesn't get any simpler. How am I possibly ever supposed to solve this? Until you realize that you can do the following little thing. And I know that you did learn this in calculus, but you probably don't use it all that much. Let's go ahead and do that right here. Let's take it from the top. All right. Let's go back up to here. The Laplace transform of the cosine. All right, Laplace transform of the cosine. So let's write it down here. Laplace transform of the cosine of beta times t was equal. Notice there's an s over beta times the result of this integral, which I just did. So I have to carry the s over beta down, times the result of what I have in here. Now the result of everything down below is what I've gotten right here. So let me open a bracket and say that what I get here is 1 over beta minus s over beta. Now instead of writing this as an integral, just realize that this is the Laplace transform of cosine beta t. So I'll just write this as Laplace transform of cosine beta times t. And then you can kind of see how it might be okay. Because what's happening here is I've got Laplace transform of cosine beta t on the left, and I've got Laplace transform of cosine beta t on the right. So I can treat it like any equation. I can solve for the Laplace transform of cosine beta t, and that's going to give us the answer. All right. So what you're going to end up having is, on the right-hand side, you're going to have, when you just distribute this guy in like this, what you're going to have is s over beta squared minus s squared over beta times the Laplace transform of cosine beta t, like this. And on the left, you'll have Laplace transform cosine beta t, just like that. And there's one square right here, because when I multiply this in, I get s over beta squared. When I multiply this into here, I get s squared over beta squared. The minus stays here. Everything stays here. So let me move over to the next board. And I'm not going to try to continue yet until I'll just recopy everything that I have. So Laplace transform cosine beta t is equal to s over beta squared minus s squared over beta squared, Laplace transform cosine beta t, like that. All right, so now what we want to do is we want to move this whole term over to the right-hand side. So what we'll have is Laplace transform cosine beta t plus s squared over beta squared, Laplace transform cosine beta t equals s over beta squared. So we just move that term over. Let me switch colors. Now you can treat this as a variable. It's like x and x, right? So we can factor it out. So let's pull it out and we'll say Laplace transform cosine beta t. And then on the inside here, we have 1 plus s squared over beta squared. And on the right-hand side, we have s over beta squared. So now you can kind of see where we're going, because here I just divide by this term here. And so what I'm going to get is Laplace transform of cosine beta t is equal to s over beta squared over 1 plus s squared over beta squared. Like that. So basically you take this thing and you divide the whole thing, it becomes on the denominator, and then you realize that because of the fact that this is a fraction, you can further write this as s over, the beta squared can go in the bottom, and then this becomes s squared over beta squared, like that. So it just basically becomes in the bottom. And so what you have then is you can multiply through, and you can say s over beta squared plus the beta squared will cancel with this one when I distribute in, giving me s squared. So the way you usually see this thing written, is Laplace transform of cosine, some number times time, is equal to s over, usually write the s squared plus beta squared. And then you just say s greater than 0. This is the Laplace transform of the cosine function. Notice that it's a function of s only. Beta is just a number. So let's say it's cosine 3t. Well, then it'll be s over s squared plus 3 squared. So it would be 9 over there. So that's what we get there. That's how we declare the Laplace transform of the cosine function. Now, how do we find the Laplace transform of the sine function? How do we find the Laplace transform of the sine function? I could just give it to you, but it's too tempting just to show you and remind you that way back as we were starting to do this whole process, way back in the first Laplace transform we did, we got the Laplace transform of the cosine was basically equal to this stuff times this integral, which we said was the Laplace transform of the sine. So what I will do then is I will kind of do a little aside. Let me see what color I should probably pick. Black. So let me kind of draw double squiggly lines here, because this is kind of a separate thing. I'll do triple squiggly lines, right? So what we learned is the Laplace transform of cosine of beta times t was equal, after all of this first integration by parts, s over beta times the Laplace transform of the sine of beta times t. But see, now we know a lot more. We know what this Laplace transform is. We just calculated it. The Laplace transform of cosine is s over s squared plus beta squared. So all we do is we say s over s squared plus beta squared is equal to s over beta times the Laplace transform of the sine of beta times t. And we just want to solve for this. That's what we want to solve for. And we know, we can see right away that since we have s on the top in both cases, these are going to cancel. And then, in order to get this by itself, we can just multiply by beta on both sides. And so I can directly write then that the Laplace transform of sine of beta times t once we multiply by beta to get it over there, is going to be beta, okay, over s squared plus beta squared. And we could just say s greater than 0, just like always, like that. This is the Laplace transform of the sine function. Beta over s squared plus beta squared. It's a lot of work. I'm not going to lie to you. And, you know, you could be asked this on a test or an exam. Mostly I did this because when you try to learn how this is derived in a book, it's very difficult to follow unless you jump through all the hoops. Because, you know, they leave out lots of critical steps, like what is he doing, how is he solving for it. But basically what it boils down to is it's a little bit of a trick. You have to just kind of have some intuition. You have to realize that integration by parts will be useful here. You set yourself up for the first integration by parts, and when you do it, everything in front drops to 0, and you end up with this integral here. And you notice that the cosine flipped into a sine in your next integral. So then you decide to do it again. And you say, all right, I'm going to do that again. I'm going to do integration by parts, again, setting this almost the same substitutions, and I'm hoping that that integral will flip back. So I get this stuff in the front, I evaluate it here, and then it turns out that this integral does indeed flip back into a cosine, which is what I get right here. All right? So because of that, then what's basically happening here, this is basically drops to 0. This resolves to a number, so then I can write kind of a summary of what I've done. The Laplace transform is equal to s over b times whatever I got here, which is what I've written down here. I've got the 1 over beta here, and I've got minus this, and then this guy turns into the Laplace transform of beta t. So basically what it happens is, whenever you do an integration by parts and then do it a second time, and the integral on the right-hand side flips back to be equal to the integral that you were trying to solve to begin with, then bingo, you've won. When you get an integral on the right, which is the same as the integral you were looking for on the left, then you can just solve the whole darn thing for that integral, almost like algebra, right? So that's what we're doing here. This integral is what we're trying to find, and we find out that it's related to itself. So then what we do on the next, basically the next couple of steps here, is we're just doing that stuff. We first multiply it through, we add this whole term on the left-hand side, factor out the Laplace transform, giving us this junk over here, and then we divide this whole term. It gets a little bit ugly. We bring the beta squared down, we distribute it in, and then we find out that this is the Laplace transform of cosine beta t. So that's basically the answer. And then we go and say, well, remember from before, when we got down to this part, this is the Laplace transform of the sine. So we summarize by saying Laplace transform of cosine is s over b times Laplace transform of sine. We plug in what we know for cosine, and then basically solve everything for the Laplace transform of sine. So again, in a lot of books, in a lot of classes, your professor or your book would probably just say, hey guys, Laplace transform of a sine is equal to this. If it's sine of 3t, it's just 3 over s squared plus 3 squared, right, if you're doing sine. And the Laplace transform of cosine looks sort of kind of similar, but it's a little bit different, and you basically apply it the same sort of way. You're getting a function of s out in both cases. They look kind of similar, but they're not quite the same. A lot of your professors, a lot of your classes, a lot of your books are just going to say, use me. And that's fine, that's totally fine, but sometimes I want to show you where things come from, because it builds your calculus skills, gets you comfortable with that Laplace integral, and then you can kind of see that the stuff doesn't come out of thin air. There is some rigor behind it, and it's not something you can do, you know, in 5 minutes, but it's something that's understandable. All right, so we're almost to the end of our road here as far as doing the derivations. I wanted to do that because I wanted to show you where this stuff comes from, but we have enough essential Laplace transforms derived so that what we're going to do in the next lesson is we're going to write them all down on the board, almost like a table of integrals. You know, we use table of integrals back in calculus. We'll have a table of Laplace transforms for you to understand, and I don't want to say memorize, but become really comfortable with. And what's going to happen is we're going to use those Laplace transforms a lot, over and over again, to solve real problems. And you'll find out that now that you know how to take the Laplace transform of the sine, the cosine, an exponential, a constant, which is the Laplace transform of 1, and also the Laplace transform of a power like t to the nth, or t to the 5th, or t to the 4th, then you have almost all the essential bases covered to do a lot of practical problems. So that's the path that we're going down. I know this course was front-loaded with a lot of heavy calculus, but but I wanted to show you how to do it because I think that's what's missing from a lot of books. So follow me on to the next lesson. We'll summarize our results in a table, and then we'll begin using these Laplace transforms to do real problems and solving real differential equations and learning how Laplace transform is powerful and useful.